Good evening once again. This is Dr. Belga Berg, faculty member at Department of CSE, AI and ML and Cybersecurity, Jane deemed to be University. Welcome to another session of Industry Connect program. I'm glad to introduce today's guest speaker, Mr. Dhananjay Das, to you. Mr. Das is a procurement and advanced analytics expert with 14 years of exposure to strategic planning, operational excellence, and supply transformation. He is a certified professional in supply management. Mr. Das has worked with IT big shots like UHG and Infosys, and he is the co-founder of Zophony IT and Consulting with a view to providing procurement, digitization, and business enhancement services to mid and small tier companies. Currently, he is the strategy and operations lead at Zophony IT and Consulting. Today, he will be talking on the topic Supervised Machine Learning Algorithms, Support Vector Machine. We are glad to have you here, Mr. Das. Welcome. Please take over the session.
Thank you so much. Welcome, everybody. I hope my voice is audible. It's clear. You all can see me.
Yes.
All right, great then. All right. So today, the topic that we have selected for our discussion is going to be supervised machine learning. Specifically in supervised machine learning, we'll be speaking about support vector machine and understand how SVM or support vector machine is being utilized in some of the day-to-day or very basic ML activities. So we'll get started with the topic. We'll understand the concept of SVM, how we can implement SVM in some of the regular activities, and we'll maybe try and implement or create a SVM program today in the class. All right. So with that, I will request all of you to stop me, ask questions if there are any, and we can take those questions while we are discussing. We'll not keep a separate Q&A session at the end. Rather, I would encourage you to stop me and ask me questions when we are discussing the topics. All right. So the agenda, what will be discussing today, what are the topics that we'll be covering today. We'll start with what exactly is SVM or support vector machine. What is that concept? And we will briefly talk about the algorithm, the background mathematical functions that is being used in SVM, the approach that SVM takes. Then we are going to talk about non-linear SVMs, because when we speak about SVMs as a tool, they support or they're created for linear bifurcation. But we are also going to talk about how we can use the concept for non-linear bifurcations. And then we'll be talking about the applications, and maybe at the end I can share a list of glossaries with you from an SVM standpoint. Or maybe after this call, I can send it to the college team, and they in turn can share it with you. All right. So that this is going to be the flow of our discussion today. So we'll start with what exactly is SVM and why we use SVM. So SVM means supervised, support vector machine, and support vector machine is being used in supervised machine learning algorithms. It's been classified as a supervised machine learning algorithm. So what exactly is supervised machine learning algorithm? An approach where we train an machine learning model with existing set of details that is there with us. So we have historical exposure to the situation. We train the model based on the data that is historically available. And based on that learning that the data gets or the model gets from the old data, it is going to now tackle the new situations. So it's like, you have been exposed to playing cricket, for last 1 year. So you know how to play cricket. And now when you are now, playing for your college team, you know how to bowl, how to bat. So you are already accustomed to the situations of playing cricket. So that's what supervised machine learning is similar to. You are being given an existing set of data with the findings, how and what was the outcome of the situations in the past, and the model learns from that detail and try and predict or try and behave similarly in the future as well. So this is a supervised machine learning algorithm where it understands or get information from an existing set of data. It trains the model, and based on the new trained model, it takes on the new set of information or the new set of data that it encounters. Why is SVM being used? SVM is being used as a classifier model. So when we say classifier model, it can both be used for classification and regression. Classification means either or. So you have two sets of groups, and what supervised machine learning does, based on the data, the factors, or the behaviors that it understands from the data, it will either classify the set of information into group A or group B. That is classification. You have groups, you have to segregate, or the model segregates the data into different groups. And what is regression? Regression is to predict a quantitative outcome. It's not black and white. Regression will always be gray. It will give you a quantitative value, a continuous variable as an output, okay, a continuous number as an output. And that continuous number is being given by the model that you are trying to use. It can be a regression fit model, it can be a decision tree model, or it can also be an SVM model. All right. So SVM is used for both classification and regression, but it's being seen because of the nature or the core algorithm of SVM, support vector machine. It supports classification activities. It supports bifurcation activities, segregation activities. That is why SVM is majorly being used for classification. I'm not sharing my screen. Is my screen visible?
Yes, it is visible.
Okay. All right. So we use SVM mostly for classification activities, and also it has the capabilities to take on regression challenges as well. That's point one. Okay. Then we're talking about dimensions of the data and what SVMs can help us achieve in terms of the dimensions of the data. SVM is specifically created keeping in mind two-dimensional data, like two features. For example, let's quickly take an example here. Let's see if we have a set of information where we have a set of information where we have x-axis and y-axis. Where we have x-axis and y-axis. Okay, and we create a scatter plot. We create a scatter plot based on the details. Okay, let me change the color. Let's say I create a scatter plot based on the values of x and y. And once I create a scatter plot for these values, the values are depicted by these data points. X or there are two categories of data. For example, let's say these are all type 1, these are all type 2. Okay, two sets of data. When we plot the x and y values for all these details, we see that the data is being bifurcated, or visible that the data can be bifurcated into two groups. When you know that the data can be bifurcated in two groups, what is the best way to create that segregation or division from a very orthodox way? We'll talk about the very concept of SVM here. The best way to segregate this data is to simply draw a line in between. If you know that these red dots are a particular set of data and then green dots are a particular set of data, to bifurcate or to segregate these data points, we can simply draw a line in between. And this is what SVM does. When you have, two dimensions, so we're talking about two dimensions of data here. This is dimension X or parameter X or, a property X, and we have dimension Y or parameter Y or property Y of the data. Let's say this is, the color of the products. So we are talking about the color of the fruit. Let's say we are trying to classify, fruits, and we're looking at the color and we're looking at the shape. Okay. So color may be, these are all objects which are, maybe yellow in color. And these are all objects which are red in color. And these are maybe, maybe these are long, and these are spherical. So maybe these are strawberries, these are bananas. We can maybe classify the fruits based on their shape and their color. So we are looking at the two aspects or two properties of these fruits. We're looking at color property and shape property. But maybe you can also add a third dimension to the data. Maybe you also want to, evaluate the taste of the fruit to understand what kind of fruit it is. Maybe just two parameters, these two factors are not sufficient to tell you what category of fruit this is. Maybe there are fruits which are red and circle, but may not be strawberries. Maybe they are cherries. They are also, spherical. They are red in color, but it's a different fruit altogether. So maybe we'll have to add a third layer of, third layer of properties called as taste here. If the taste is sweet, we may, classify it as a cherry. If it is, tangy, we can call it a strawberry. Okay. So, all these parameters, and SVM was, intrinsically created. It was developed keeping in mind two-dimensional data with two properties. Just create a straight line in between, and we are able to bifurcate anything to the left of this line. These are strawberries. Anything to the right of this line, these are bananas. It's as simple. But maybe we want to add another parameter. We want to add another feature. The third feature here is taste. So the dimension of the data increases. From a two-dimensional data, we are now trying to work on a three-dimensional data. When we are working on a three-dimensional data, when we're working on a three-dimensional data, the third dimension here, let's add, the taste of the values. So when we're working on a three-dimensional data, instead of this straight line that we have created to bifurcate the data points, the new bifurcation will be in the form of a plane, because just a straight line cannot, segregate the values in a three-dimensional space. A line will not be sufficient to segregate the values in a three-dimensional space. So for example, if you have a, cuboid or a cube, and you want to, cut the cube into two pieces, can you cut the cube into two pieces just with the help of a straight line? Or you would actually need a plane. Maybe you use a axe or a saw to, or a plate to put it between the cube and, bifurcate it into two parts, cut it into two parts. So if it is a cube, to cut it, you cannot just cut it with the help of a straight line. What you'll have to do, you'll have to use a plate here, which is a two-dimensional plane. So based on the dimensions of the data, if it is a three-dimensional data, we'll use a plane. If it is a four-dimensional data, maybe we'll have to use a three-dimensional object in between to bifurcate or segregate the data. For an n-dimensional data, what we'll have to do, if it is an ND array or a data with n dimensions, we'll have to use a hyperplane. Okay, instead of just a straight line, which was able to bifurcate the data in case of a two-dimensional data sets, for a three-dimensional data sets, we were, we were able to bifurcate the data with the help of simple planes. For a n-dimensional data set, we'll need a hyperplane. Okay, because the dimensions of the data is more. And we are just looking at just two aspects of the data sets here. We are looking at only two types of data sets here, like, or two fruits. Specifically we are talking about bananas and strawberries. If we have more than two types of fruits, how we can manage them? So that is also a problem, because when we are talking about bifurcations can only happen in case of two. Bifurcations means half of, you're segregating the data into two groups. But when there are more than two groups, how do you manage that data? Okay. For more than two groups, what SVM does is something called as one versus many. Okay. The approach it uses is called as one versus many. What it does is, it if there are 100 sets of data or 100 types of food that we're trying to classify, what it will do, it will classify first one type of fruit and tell that all the remaining 99 are not type 1. So for example, it classifies bananas first, and all the remaining 99, it says it's not a banana. And similarly, for from the remaining lot of 99, it will segregate one part. It will say, like, out of the 99, part 1 is strawberry and the remaining 98 are not strawberry. Then again, from the 98, it will segregate part 1. It will say, like, yes, this part is mangoes, and remaining 97 are not mangoes. So what it does is, from that entire data set, it actually classifies one type of fruit or one type of data set in one go, and it kinds of separates or segregates the remaining all other types of fruits in a different bucket. Okay, SVM by default can only work on two sets of data or two classifications, binomial classifications we call it, because it can classify only between 0 and 1, or type A or type E. So SVM actually is a binomial classification systems designed for a two-dimensional data, but we have been able to develop the core algorithm to help us classifying data which is more than two dimensions and more than two types of data, or more than two sets of data. Okay. So multi-dimensional data sets and array data sets and data sets with multiple classifications can also be classified with the help of SVM model. Okay. And then we'll be briefly talking about what is the SVM algorithm, how it classifies the data. So let us look at the old example. So let's say, like, all these blues are type 1 and all these greens are type 2. So if somebody has to bifurcate these groups into two, as we discussed, we can simply draw a straight line in between, and we can tell, like, everything on the left of this line is type 1, everything to the right of this line is type 2. But there are multiple options for us, or multiple lines that we can create in between this type 1 data and type 2 data to segregate them, right? So we can maybe create this red line, we can create this black line, we can draw this green line, all these different lines, or maybe hundreds of other lines also in between them, which will be able to segregate this data. So there are multiple options or multiple ways we can segregate this data with the help of different lines. So when we have so many different options, which is the best option? And that is where SVM comes into picture. It creates a line in such a way that the distance between it creates this line in such a way that the distance between these support vectors, the end points, these are all the blue dots, group 1, these are all the green dots, group 2. The support vectors are the data points which are closest to this line that SVM creates. So objective of SVM is to create this line in such a way that the margin between these support vectors, the closest data points from each groups, the closest data point from group blue and the closest data points from group green, the distance between this plane or this line and these support vectors or the closest data points is maximum. If this line is towards the left of what we are seeing here, if the line is, let's say the line is here, the line was created here, this will be closer to the blue dots. So we are not, maximizing the distance between the blue dots and the line. If we draw this line here, it will be closer to the green dots. So we are not maximizing the distance between the line and the green dot. So we will create this line in such a way that the distance between these blue dots or support vectors from group 1 and these green dots, which are support vectors from group 2, and the line, the bifurcation line, which is called as the optimum hyperplane. All these lines that we are seeing here, this is one hyperplane, this is one hyperplane, this is one hyperplane, because all these planes are able to bifurcate the data, right? So we're considering a n-dimensional data set here. So all these hyperplanes are able to bifurcate the data. But because we have multiple options and multiple hyperplanes, which is the optimal hyperplane, which is the hyperplane that we are going to use from an SVM standpoint. We are going to use this line, which is able to get us the maximum margin. And when you look at it conceptually, if these are a set of information, these are set of information, how would you want to bifurcate them? You want to create a line, but you would want to create a line in such a way that the width or the gap between these two groups, this group 1 and group 2, is maximum. When the gap between these two groups are maximum, we can clearly tell if we are getting a new set of data in future, we can clearly tell if that new set of data is from group 1 or group 2. Because the distance or the gap or the width or the margin between these two data sets is more. If the width is less, then there can be confusion if a new data set is from group 1 or group 2, because the difference is not much. The margin that we are looking at is not much. If the margin is narrow, there is a possibility that we can misclassify an object from group 1 to group 2. Let's like this margin was, say, only this narrow. All right. So anything which is, say, here, we don't know if it is group 1 or group 2 because the margin is very narrow. These points, we're not sure if these are group 1 or group 2. These points, we're not sure if these are group 1 or group 2 because the margin is narrow. The difference is not much. When the difference is not much, we cannot easily classify, or the model cannot easily classify the group type. So the objective is to create a line in such a way that the margin is maximum, the width is maximum. So, any new set of data can easily be classified into group 1 or group 2. That is point number 1. And one other important factor that we have to keep in mind is, the involvement of the remaining data points. So we're talking about the support vectors, the data points which are closer to, the optimal plane. We're looking at, or the optimal plane is created in such a way that this margin is maximum from the support vectors, right? What about these additional data points? How are these additional data points impacting the position of the hyperplane? It actually does not impact how a hyperplane is created. And that is very peculiar about this SVM model when we compare it with all other models. All other models kind of take information from all the data points which are there in the training data set, and it creates a model based on whatever information is available. More information available, the training model will be more efficient because it has more training data to learn from. But this optimal hyperplane is not dependent on any other data points apart from the support vectors. Apart from these data points, it doesn't matter if this a blue dot was here or was here. The hyperplane position will not change. If this green vector or this green data point was here or it was here, the hyperplane will not change. This optimal hyperplane's position will not change. This optimal hyperplane's position is only dependent on the support vectors, or the vectors or the data points which are nearest to it. So that is, that is why, SVM is being widely used, because it does not, put a lot of constraint, and it doesn't take a lot of resources, because, the optimal plane is only dependent on this. In this case, it's dependent on only these 4 dots, 0.1, 0.2, 0.3, and 0.4. It is not dependent on any other thing. So because it is not dependent on any other points, the resources that it consumes to kind of run this program is very less. All these remaining data points are immaterial for the SVM model. This SVM is very resource efficient from that point of view. And then we are going to talk about, I don't know, we are running out of time. So I wanted to talk to you about the non-linear SVMs, because we saw that, how SVMs work. They create a straight line between 2 different data points, and that straight line or that bifurcation is the differentiation between group 1 and group 2. But sometimes there are, in real life, we will hardly see data points which is as linear as it is. Data points are actually non-linear. That when we collect information in real life, we'll come across non-linear data points. So how do we use SVMs in that case? We use 2 concepts. The first concept is called as a soft margin. How soft margin works? Soft margin works with the help of, by giving tolerance limits. So here, what we do, we have a soft margin whose value is 1. That means we are intolerant to misclassification. We will create this model in such a way that, everything which is blue, will try and create the margin in such a way that everything which is blue is classified correctly, everything which is green is classified in the other group. No matter how narrow we have to make this, the SVM model, or the margin be. Here the margin is very narrow, but we have been able to, segregate almost everything which is blue into one group, everything which is green into the second group. We have done that, but we have created a very thin margin. When the margin is very thin, the probability of misclassification in the future increases. Any data point which is here might get misclassified as green, or any data point which is here might get misclassified as blue, because the margin is very, very, very narrow. The margin of error is very narrow. The other way is to use a lower value for soft margin. When we are saying a low value for the soft margin, that means we permit the data to make mistakes, to make misclassifications. It's okay if few data points are left out. When we are looking at here, this is my optimal plane. We are seeing this blue value to the right of optimal plane. That means the model is actually classifying this blue value as green, but I'm not trying to overfit my model by just looking at this one data point. Was I adding more pressure to the model? Yes, definitely, because I was reducing the margin. Here I have increased my margin, I have widened my margin. Okay, but I am ready to take a little bit of risk from a classification standpoint. If few classifications are going wrong, which in this case is this, I'm still able to cope up with it. I'm still okay with it. My tolerance is there. So soft margins value higher means low tolerance for misclassification. Soft margins value lower means I have tolerance for classification. Please increase the width of my margin. Okay. This is this approach. And then we use a kernel transformation approach. And this is very interesting when we are working with non-linear data sets, because here what we are doing, we are just trying to use a method. We are still using a linear line. We're still using a linear line, a straight line. It is not truly a non-linear approach, but yes, we are adding tolerance values to the linear approach, and we are able to work with non-linear data sets with this approach. But this kernel transformation is nothing but transforming the existing data set, transforming the attributes or features of the existing data sets. Okay, so that is kernel transformation, core transformation we are making. We're making transformations to the data sets so that you can implement an SVM which fits for linear bifurcations, for linear classifications, even in case of non-linear data sets. So let's take this example here. So let's say we have data points here, -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. This is my data set. This is the plot that I've created, the regression plot that I've created, the distribution plot that I've created. How can we create a straight line to bifurcate the green point and all the remaining yellow points? Can we create a straight line? Can we add a straight line to this data set? This green is of one group. All these yellows are of different groups. And these are the values. These are the values of X axis and the Y values. How can we create a straight line to bifurcate these groups? We cannot, because obviously we have to add a circle in between to separate these groups. So maybe this is group 1, whatever is there in this circle, it's group 1, whatever is outside of this circle is group 2. But SVM doesn't allow us to create this non-linear diagrams, non-linear structures, non-linear bifurcations. So what we do, we make use of kernel transformations here. So what we are doing here is called as a polynomial transformation or a poly transformation, where we are playing around or fiddling with the degree of the factors, the value, the degree of these factors. For example, what we are doing, we're keeping the Y value same, but we are squaring the values of X. So what we have done, we are doing a square of -2, we are getting 4. So the first data point that we are going to create is 4 -2. Where do I have? Yeah, 4 -2. This is my first data point. What is my second data point? -1 squares, which is 1 -1. So we have X value 1, Y value -1. Then we have 0, 0 square is 0, and we have 0, 0, 0 is the third data point. The fourth data point is 1, 1, and the fifth data is 2 square 4, 2. So we have plotted these values now into a different graph, and it gives me this, this new diagram, this new plot. So with these values, with this new plot, is it possible to create a straight line to bifurcate the data? Obviously, the answer is yes. We can simply draw a straight line here. We'll obviously have to look for the optimal planes. This is one of the hyperplanes. We'll have to look for the optimal hyperplane, but this is one of the hyperplanes with the help of which we can bifurcate the data. Anything to the left of it is green, anything to the right of it is yellow. So what we have actually done here, we have transformed the existing data set. This was my existing data set. I have transformed my existing data sets with the help of polynomial transformations to increase the degree of some values. We have increased the degree of all the X values by squaring them. We have increased the degrees of all the X values by squaring them, and we get the new X values. And we use the old Y values and create a new plot of this data. And then with this new data set, with this new features, these are new features, these are derived features for me. This 4, 2, 0, 1, and 4, these are the derived features from my original data set. My original data sets did not have these values. I recreated these values by transforming my original values, and with these new derived recreated values, I'm creating a plot for this, a model for this, and on this model I can actually use a what we call it is a linear bifurcation, a linear segregation. And when we translate this model back to my original data set, this straight line now appears as a circle. We have not changed anything. We are just transforming the data. We are making adjustments to the data. After making adjustments, we are able to create this linear bifurcation. And after that, when we translate this data back to my original form, the linear transformation now, or the SVM model now, looks like a curvilinear model or a non-linear transformation, a non-linear SVM model. So this is how we can use SVM models for non-linear data sets as well. Okay. Any questions, any doubts on the fundamentals, the basics of SVM? If not, then we can move on to application of SVM. We can create a real life, a Python program to kind of work on some real life data sets, and let's see how it is working on SVM. All right. If not, then we'll quickly move on there. What I'm going to do here, I'm opening up my Jupyter notebook, and on my Jupyter notebook, I'll be creating a new, transformation. A new SVM model. Okay, I'll be creating a new SVM model. So for this new SVM model, what all I have to use? I use different libraries which are already available on Python. The core library to create this SVM model is going to be scikit-learn. Okay. Scikit-learn is the library, the analytical library from Python, which can be used for multiple, machine learning algorithms, for creating different machine learning models, starting from regression, models to decision trees to SVMs and so on. So we'll be using the same scikit-learn here also. So we are going to import sklearn, and from sklearn we are going to import SVM. From scikit-learn, sklearn, import SVM. So SVM is the support vector machine model with the help of which we were going to create the model now. Okay. And we are also going to have or use a pre-existing data set which is there in the scikit-learn model. Okay. We are not going to import our own data set. We are going to use an existing set of data which is there for in scikit-learn for practice. So from sklearn, we are going to use or import data set. And then for the plotting activities, we are going to import matplotlib, plt. Okay, we are going to import matplotlib, and then two small things. We will not be actually using a data frame. We are not going to create a data frame because we are going to use a pre-existing, ND array which is already there in the data. We are going to use it directly from scikit-learn. But I wanted to show you how we can visualize the data or look at the data from a data frame standpoint, because like this ND array might not be easy for us to understand. So we are going to quickly import pandas so that we can look at the data frame. We can create data frame, this existing data set, and look at it. And then from sklearn, we are going to import model selection. Import test, the train test, because we are going to split the data into training data and testing data. So we are going to import train test split from scikit-learn. So these are the different libraries which we are going to use for this exercise. We run this, and then the data set that we are going to use is the digits data set. Data sets. Yeah. So we are going to use the digits data set. So the data sets that we're going to use is the digits data set. We are going to load digits. All right. So we're going to load digits here. Digits data set is actually what we call it. It's the OCR data sets. It's an optical character recognition data sets where all the numbers starting from 0 to 9 are being scanned. There are different samples of the same number 0 to 9 that's been collected from the handwriting of different people. And all these values are scanned and then transferred, into a pixel model. And all the pixel values are being captured in this data set. So let's load this data set. Let's load this data set. And then what we can do is let's understand what this data set is. Digits dot we'll describe this data set and tell us what this data set is all about. This is an OCR data set for handwritten digits, and it has 1797 instances or 1797 rows in the data sets and 64 attributes or 64 dimensions. If you're talking about two-dimensional data sets, this data set has 64 different dimensions or 64 different properties, attributes, and 1797 different rows. 1797 different rows. What has been done in the background, the pre-processing of the data that is being done, what is being done is like an 8 by 8 integer pixel of the values is being created. All these handwritten values are scanned, and a pixel value for all these 8 by 8 images is being stored in this data set, in this different 64 attributes or properties. So with that, let's do something. We can print the shape of this data. What was the data set? Digits. So we can print digits dot shape. We can see the shape of this data. It has 1797 rows and 64 records, like we discussed. So we looked at the shape of this data, and let's now move on to creating the model based on this data. So before creating a model based on this data, we looked at, yes, this data has different rows, different columns, different features are there, different images are there. So we are going to quickly let me plot one image for you. So what we are doing, we'll change the plots into a grayscale value, and then let's use matplotlib here for these digits. And what we are going to do on this digits, let's print or see how one of these images are looking like. plt.gray. Let's see how this follows. Or what we can do is plt. Just one sec, there is a little noise here. So we can do it like show what we'll be doing digits, and then in this digits we are going to get the images, and we'll be using one of the images. Let's see if we are able to run it. Gray is somehow not working. Or what we can do is we can maybe print the target names. Let's print digits dot target names. Let's print these values, and let's see if we're getting the target names. Yes, the targets are 0 to 9. So we have the target values. The target values or the output values, the Y values are all 0 to 9. So we have got the target values here. And the X values are the feature names. So we can see the feature names also. What are the X values? We can see the X values as feature names. Let's see all the feature names. Yes, we have all these 64 different features or the feature values. Now we'll maybe split the data into train test split. So what we are going to do, we are going to create an X test, X train, and X test, then Y train and Y test. You call it with whatever variable names you want. And then we're going to use scikit-learn's test train split view is something that we're going to use. We're going to train test split. We'll be doing a train test split on this data. And on this data, what we are going to split, we are going to split the digits data set digits dot features, right? The X values are features and the Y values are digits dot target, right? And then we have test size, how much data we would want to use for testing purpose. Let's say the test size is 0.8. Sorry, the test size maybe 0.2. We want to keep 20% of the data for testing and remaining 80% data for training, and random state that we are going to use to define what values to be selected at random. Let's use it as 1, or we can use it as 0, whatever you want to feed. You have a feel like you can use a random state. Feature or it's not feature data. Yeah, so we have the training data, test data, training Y data, and test Y data ready from the data sets and the target values. The data sets are the X values and the targets are the Y values. Now we are going to create a support vector machine model, SVM model. So for this SVM model, what we are going to create, we'll have to create a classifier. Classifier here is fit, or what we'll be doing, svm.svc. svc is support vector classifier. Like I mentioned, we can use support vector for both classification and regression activities. We are going to use svc, which is for the classifying activities, and we'll be having this, right? And then we are going to fit these values. So what we are doing, clf dot fit these values. For what are the values? We will be using the training data, X train and Y train, right? X train and Y train will be fitting these values. We have created a SVC model based on the X train data and the Y train data. And now let's predict the values. Let's print the predicted values. Let's print, what do we call it? CLF dot predict. And then we'll be predicting the values based on the X test data. We'll be passing on the test data to the SVC model or the SVM model, and we'll be predicting the values. Let's see what are the predicted values that we are getting. Okay, we used a small x here. So the predicted values are these, and let's print the predicted values of Y spread, and let's see if there is any difference. Y test, okay, not the predicted values, the test values. So you have the predicted value or the test values of Y. These are the predicted values of Y, and these are the actual values of Y. So 1 was actually predicted as 1. If we want, we can change if you want to add a margin, for example, in this case, we are getting accurate data. All the classification seems to have been done accurately. Okay, so if the classification was not accurate and it was not confined within the linear set of classifiers that we have, what we could have done, for example, let's add C. C is nothing but the soft margin. So we can add a C or a soft margin values. So let's say we are adding the soft margin that we saw as 1 in one case. Let's add a soft margin of 1 and let's see how is my classified value coming now. When I add a soft margin here of 1, the classified value or the predicted values that I'm getting is little different. What the difference do I see for one of these values? Let's see. Am I getting? Yeah. So here, if you look at the last 3 values here, we are getting 999, but in reality, these values are 998. By increasing the classifier C or the soft margin, I'm actually getting some errors. The data is overfitting because the differentiation is now very narrow. We can also, add other parameters like gamma. Gamma is for, the kernel transformations. We can add gamma values and see if the kernel transformations is making any difference. Yes, the kernel transformation is making a lot of difference, and all these values are actually predicted as 5 because we have made kernel transformations to the data. We have made feature transformations to the data, and the predicted values are not getting accurately predicted. We're getting the predictions as 5, but the actual values of these test data set is 150 or whatever the values that we had in the test data set. So you can play around with these gamma values, the C values, and the type of kernel transformation that you want to use, and you get the actual values. If the prediction is not accurate, you are seeing a lot of difference, then maybe you can add a value of C there. You can add a value of gamma there to take care of the soft margins, to take care of the factorial what do we call it, dependence of the data. And you can then play around with all these different parameters of the SVM learn model to get the accurate prediction. So this is how an OCR model actually works. So OCR model will, we have trained an OCR model based on different features or different data sets that we got from the source data here. Okay. So what happened, 1700 odd, handwritten numbers were scanned, and the scans were, changed to all these values like pixel values, pixel 00, pixel 012, pixel 77, all these 74, 75, or 64 different values or 64 different attributes were derived from the pixel or the pictures that was clicked from the handwritten numbers. And from these pixel values, we are able to predict what these numbers actually are. Okay. So we have trained the data or the model based on these 64 different pixel values. And when we pass on the pixel value for a new data point, it is accurately being able to predict what this number is. Okay. So here machine learning is or computer vision. When we talk about computer vision or machine learning, what it actually does is, based on all these historical pixel rates, it fine tunes its model. It learns from the model and classifies the values, what these numbers are. And when a new set of pixel values are passed on to it, it is able to use that learning from the past to predict what these numbers actually are. So this is how SVM model can be implemented in Python, and we briefly understood about what SVM model is all about. What are the different features of an SVM model? Why do we use it for classification? What are the soft codes? The basic algorithm of SVM model. So we briefly spoke about that. If there are any questions, please feel free to shoot them now. Any questions, any doubts from you guys? Okay. No questions, no doubts. All right, everybody. Then I think we are good from my side.
Up. Yes, sir. Okay, so let's wind up this session. Students, please fill in the survey form before you leave. The link is in the chat box. So as always, thanks are due to Department of Computer Science and Engineering, AIML and Cybersecurity, and Futurance Technologies for ensuring that our students get proper industrial exposure through these interactions they have with industrial experts. We are grateful to our guest of honor, Mr. Dhananjay Das, for brilliantly explaining support vector machine to our students. I thank Dr. V. Vivek, the head of the Department of Computer Science, Engineering and Artificial Intelligence and Machine Learning and Cybersecurity, for eminently spearheading the departmental activities. I also thank our team of faculty members for guiding our students in academic and co-curricular activities. Dear students, thanks for participating in the session. See you all next week with another wonderful session of Industry Connect. I think we can close the session now. Good night, everyone. Thank you, Mr. Thanajay, once again.
Thank you so much.
Thank you, sir.